corner with not n delta.
That's the logo of the Istituto Nazionale di Alta Matematica, Maths Research Institute in Italy. Yeah.
Very classy. Okay, I will. Okay, so this is
okay. So we are online.
Exactly. So the recording is launched. Yeah, I guess we said we resume at 5. We can resume now. So for this second talk today, we have Alessandra Caraceni, who will give some bound on the edge flip for mixing time and of edge flip Markov chains and triangulations and random planar maps. So just what we were doing before, but another aspect. We are listening to you.
Indeed. Thank you very much. Thanks for the invitation again. Thanks to Alessandra for giving the first pass of this double talk. And I'll just get back into it, straight into random edge flips on quadrangulations again. So just in case, let me repeat the model that we're working with for 1 second. So I'll have my state space Qn be the set of all possible quadrangulations of the sphere with n faces, rooted. So again, there's a distinguished oriented edge. And we're considering the Markov chain of edge flips on this state space Qn. So we're selecting an edge uniformly at random, and now a quadrangulation with n faces has exactly 2n edges. And this edge, as in this picture, it can be rotated 1 step clockwise or 1 step counterclockwise is the way I'm saying it. But with probabilities 1/3, 1/3, 1/3, I'll rotate this edge 1 step clockwise, 1 counterclockwise, or just leave it the same. So this is the Markov chain that we're considering. And Alessandra already stated our results, which are a lower bound, which is the one he talked about, and an upper bound for the relaxation time of this chain. And what I'm going to do in this talk is at least attempt to give you an idea of how to construct a complete proof of this upper bound for the relaxation time with a sort of the specific argument that is, I hope, interesting, among other reasons, because it would apply to a number of possible variants of this model. So certain edge flip chains on, for example, 2p angulations or simple triangulations of the sphere, or as Alessandra mentioned before, you can do edge rotations on general planar maps. But this argument would also apply to certain chains on plane trees or even on triangulations of the n-gon that we mentioned in the very beginning. So how does our proof of this upper bound go? We need sort of, I would say, 2 main ingredients, although one could probably say it's 3 ingredients. And let me mention in the very beginning ingredient 0, which is some sort of enumeration result for our state space. So in this case, we want to know how many quadrangulations, rooted quadrangulations of the sphere with n faces there are. And the answer is very well known. This is a number that we know explicitly. It's related to the n's Catalan number, but the result that we will eventually need in this proof is asymptotics for the cardinality of Qn. And in particular, we want to know that it's, well, they're a constant times an exponential factor in n times some sort of polynomial correction in n. And a result of this type is true for all the objects that I drew at the bottom of this slide. But as we mentioned before, it's definitely not true or known, for example, for lattice triangulations, which disqualifies this sort of approach for example, that case. Anyway, ingredient 0 being mentioned, let's go to ingredient number 1. That is sort of a standard method for estimating the relaxation time, that is constructing some canonical paths. So let me try to briefly explain to you how the strategy of canonical paths works for giving upper bounds for the relaxation time of, let's say, a reversible Markov chain. So the idea here is for each pair of objects in your state space, X, Y, just build a path gamma of XY that's made up of single transitions of your Markov chain of non-zero probability. So in our case, X and Y would be 2 quadrangulations of size n, so with n faces, and gamma of XY would be a path going from X to Y via single non-trivial flips. Now, if you build canonical paths for every pair in your state space, then if you consider a single flip, a single transition of your chain, you can look at all possible paths of the form gamma of XY that actually use that transition. And if you are able to say essentially that there are few paths using that single transition, then you're effectively excluding the presence of relevant bottlenecks in your chain. And this sort of estimate is going to allow you to give an upper bound for the relaxation time of your chain. So let's actually quantify this. And we do this via a bound in the form given by Diaconis and Saloff-Cost. So an upper bound for the relaxation time is given by a first factor that you see there, the maximum over all possible chain transitions of that first factor, which is really the inverse of the natural capacity of that chain transition. And a second factor that is the sum over all pairs XY, such that that single transition, yellow to blue, features in the canonical path you've chosen from X to Y of pi of X, pi of Y times the length of the path. So essentially that is telling you what load your network of canonical paths is requiring your transition to be able to bear. This is the upper bound that you get, at least let's assume that the Markov chain is reversible, which is indeed the case for us. Alessandra already told you, I think in this case as well, that this chain is reversible with respect to the uniform probability measure on the space of quadrangulations. And so these pi of X, pi of Y, etc., we can just replace by 1 over the cardinality of the state space. So let me make this formula a little simpler by simplifying that. And now what we use is a slight variant of this. So of course, instead of just selecting a single deterministic canonical path, gamma of XY for each pair XY, you could have gamma of XY just be a random path made up of single positive probability transitions of your chain. And if you do that, everything, all that will change in that formula is just you'll need to compute an expectation instead of having just the deterministic length of gamma of XY. All right. Now, let me manipulate this bound a little bit further, just so that it's ready to use towards the end when we will need it. In fact, I'll end up being a little bit lazy, perhaps, and just giving a uniform bound for the length of my random path gamma of xy as a function of n. So I'll just get that out of the expectation as a quantity L of n, so that inside that sum, the part that will end up being more difficult to estimate is this sum for xy in your state space of just the probability that a single fixed chain transition features in the random path gamma of xy. So this is all I want to say for now about the method of probabilistic canonical paths. I will now introduce you to ingredient number 2 in this proof, which will perhaps be a little bit more unexpected, which is what I will call, let's say, a uniform reduction scheme for quadrangulations. So what do I want to do? Let's say I have a fixed quadrangulation of size n with n faces. What I want to do is obtain from this a quadrangulation of size n minus 1 by performing a specific type of operation. That is, I want to reduce this quadrangulation by taking a face of the quadrangulation and just collapsing it without touching anything else about this quadrangulation. So I can take this face and collapse it by identifying 2 of its vertices and gluing its boundary onto itself. All right, so this will be what I will call a face collapse. Let me say really briefly, as a matter of fact, quadrangulations also have degenerate faces that, instead of having a boundary of length 4, have a boundary of length 2 and an internal vertex and edge. You can see one such face in that picture. You can also collapse those, and it's even easier. You're just going to erase the internal vertex and edge and glue the 2 edges of the boundary to each other, thus collapsing that face. Now, what I would like to do is give a random reduce operation on this quadrangulation. So I will collapse a random face, not a uniform random face. I will then discuss how to choose which faces to collapse, so that the reduction of this fixed quadrangulation is some random quadrangulation in Qn minus 1 that differs from the blue quadrangulation by a face collapse. Now, what do I want from this random reduction operation? I want that if I apply this reduction to a uniform quadrangulation in Qn, then what I obtain is a uniform quadrangulation in Qn minus 1. So what I'm saying is that I would like a way to couple Un and Un minus 1 in such a way that Un minus 1 is always obtained from Un by collapsing some face. All right, and I'll call such a random reduce operation a uniform reduction scheme for quadrangulations. Now, first of all, let me explore a couple of sort of trivial features of a reduction scheme that are exactly those that we'll end up using in the proof. So something that we can definitely do is write, for example, the sum having fixed x in Qn, the sum over all y in Qn minus 1 of the probability that reduce x is y. And you should be able to immediately tell what this is. This is clearly 1, right? Now, if I sum over x in Qn as well, that will clearly be cardinality of Qn. And what I want to say at this point, first, well, rather than think that I'm going to say about this, if I take that sum for fixed y, summing over x in Qn, the requirement that this is a uniform scheme means exactly that that sum should be the same, whatever y is. It should not depend on y. So what I'm saying is that if I just take the sum for x in Qn, that is normalizing by cardinality of Qn minus 1. And this is essentially all I will need about this reduction scheme. In fact, I'll need an easy consequence of this same argument, that is, what happens if I sum over x in Qn the probability that reduce k times of x is some fixed y in Qn minus k. And of course, what you get is cardinality of Qn over cardinality of Qn minus k. And now, if you have a little bit of temporary space in your brain, you could put this formula there. Eventually, we'll pick it back up and use it. And it will be involved in the crucial estimate of this proof. Now, this being said, I wanted to say a little more about this idea of reducing quadrangulations, or more generally, reducing maps in this uniform way. One first thing to say is that, of course, I can think of this, if I want, as a growth scheme rather than a reduction scheme. So what I'm saying equivalently is that I'm trying to couple a quadrangulation that is uniform in Qn minus 1 with one that is uniform in Qn in such a way that essentially the larger one is obtained from the smaller one by just growing a single face at one random location in the smaller quadrangulation. And so the question that I'm asking myself, at least to begin with, is whether there exists such growth scheme for quadrangulations, whether you can generate uniform random quadrangulations iteratively in this way by adding one face at a time. And now the answer for quadrangulations is yes. And here we can comment a little bit more, especially for people who haven't worked with quadrangulations or planar maps before, on why we're doing this proof for the case of quadrangulations, at least at first, and why that is an easier case to deal with. And the reason for that is essentially Scheffer's bijection, or Scheffer type bijections. The thing is, you have an explicit bijection between rooted pointed quadrangulations of size n with a set of labeled plane trees. Now, I'm representing the set of quadrangulations with n faces on the left and the set of all plane trees with n edges on the right. The bijection is not between these sets. There's some extra structure on the left and on the right, but you can interpret it as sort of a many-to-many correspondence for these two sets. And this is all that we'll end up needing, actually. And now, if you think of this reduction operation, it so happens that erasing a leaf in the plane tree on the right side corresponds to collapsing a face on the left. Let me also comment on the fact that the converse is not quite true. So not all face collapses for quadrangulations correspond to leaf erasures for plane trees. But if I have a reduction or a growth scheme for plane trees that consists in growing a leaf at a random location in the tree, so from some random corner of some random vertex, that will give me a growth scheme for quadrangulations. And let me take one more step to make it potentially even more apparent how you would go about obtaining such a growth scheme. You can always think of plane trees as full binary trees instead. So a tree like the one on the right, where at this point, you very clearly see a recursive structure, right? And so the thing is, growing a leaf in a plain tree is exactly equivalent to picking a leaf of your full binary tree on the right and just making it into an internal vertex by growing two children from it, a left and a right child. All right, so how would you obtain a growth scheme for full binary trees? Well, one would want to exploit the clear recursive structure. What you're going to do is essentially grow a tree by deciding whether to grow its left subtree, so the tree of descendants of the left child of the root, or growing the right subtree, the tree of descendants of the right child of the root. And it turns out that you can actually build a growth scheme iteratively this way by just choosing whether to grow on the left or the right at each step with a probability that only depends on the sizes of the left subtree and the right subtree. The fact that you want this to be a uniform growth scheme will give you equations for these probabilities P of NL, and you're actually able to solve these equations explicitly. So if you want, you can write down rational functions that represent the actual probabilities P of NL for every N and L. All right, this works very well for binary trees. How far can you go though? And the answer is given by a very nice paper by Lukschak and Winkler from 2004, which in my language tells you that there exists a uniform growth scheme, not just for full binary trees, but for full d-array trees. And now let me make a couple of remarks. So in order to prove this, of course, what you'd want to do is again exploit the recursive structure of d-array trees. You'll need to obtain the existence of these growth schemes inductively, but this time you're not, at least directly, quite able to solve the equations that you get. You can prove existence via max flow min cut type of argument and show that you obtain actual probabilities and iteratively are able to build your growth scheme. Now, using this result, we can go further than just quadrangulations. One step further is considering two p-angulations, so not quite general p-angulations, but maps with faces of fixed size, of fixed perimeter, of fixed even perimeter, okay? And in this setting, the role of plane trees is taken by objects called p-mobiles, and the role of the Scheffer bijection is taken by the Boutier di Francesco Guiter bijection. And these p-mobiles, you can actually link to full p-array trees. And again, exactly as you'd like, growing a full p-array tree corresponds to growing the mobile, which in turn corresponds to performing certain types of reverse phase collapses in the two p-angulations. And so thanks to the Lukschak and Winkler result, we're able to obtain growth schemes for two p-angulations. I wanted to say a little bit more because I think at least it would sound a bit strange to me in the beginning that we're discussing quadrangulations in particular, and perhaps the most natural analog in a map setting of the initial triangulation walk that Alessandra talked about would be on simple triangulations of the sphere. Obtaining existence of a uniform growth scheme for simple triangulations of the sphere is harder, there still is a link to a nice tree-like structure, and in particular with objects called blossoming trees via a Poulalon-Scheffer bijection. Here again, these two sets actually have a many-to-many correspondence, not a bijection between them. And what we were able to do with Alessandra in a very recent paper is link blossoming trees with pairs of full 4-ary trees. And with an extra layer of max flow min cut, you're able to then rely on the Lukschak and Winkler result in order, oh yes, and I wanted to say, yeah, growing these full 4-ary trees corresponds to growing blossoming trees, which corresponds to growing not one face in the corresponding simple triangulation, but two faces. After all, there's a parity issue here. So face collapses for simple triangulations are going to be collapsing two adjacent faces. So in this case, you're growing two adjacent faces instead. And yeah, so our final result is that there exist indeed uniform growth schemes for 2p angulations of the sphere and for simple triangulations of the sphere. And you could use those to prove similar upper bounds for the relaxation time of edge flip chains on these planar maps. However, what I'm going to do from now on is go back to quadrangulations, since there is a little bit of ad hoc combinatorics that you have to do depending on the model. And but it will hopefully be clear how the argument can in fact be generalized given these ingredients that I've explained to you so far. So if you are tired of bijections, that's fine. We're done with that for the rest of the talk. And the rest of the talk will be devoted to putting these ingredients together. I want to give you an idea of how to build good canonical paths for edge flip chains on these various models of maps. So suppose you have two quadrangulations of size n, x and y. We want to build a path of flips between them. And the main idea is going to be that what I want to do is, and I'll give you here a sequence of intermediate random quadrangulations that I want my path gamma of x, y to go through. What I want to do is essentially reduce the quadrangulation x and in another region of my intermediate quadrangulation, grow the quadrangulation y until x is no more and all that I see is y. And in particular, the way I want to reduce the quadrangulation x is exactly via my reduce operation. So the intermediate steps of this path, sort of keyframes that I have to go through, if you will have x first, then reduce x, which has n-1 faces, reduce x twice, etc., until they have nothing relating to x anymore. And on the other side, sort of, I want to have in reverse order, y, reduce y twice, etc. All right. Now, these are, say, reduce k of x and reduce n-k of y are two quadrangulations, one with n-k faces and one with k faces, so n faces in total. But what I want to explain to you is how I'm going to build a single quadrangulation out of these two quadrangulations. And the way I'm going to do that is actually simple. So let me show you. So if you have these two quadrangulations, reduce k of x, n-k faces, and reduce n-k of y, what you could do is just take an X-Acto knife, cut each of them along the root edge. That will make two holes in your two spheres. And now glue the brown sphere to the green sphere along the boundaries of the holes. So you have a cycle of length 2 involving the root edge, along which those 2 quadrangulations are glued to make 1 quadrangulation with n faces. So these are my random keyframes that I want my path to go through. So what's next? Well, I still need to get from one keyframe to the next keyframe via single edge flips. And what am I going to do? So what I want to do, let's see. Okay, I let it run, but what happened there was I had one face in my brown region of this quadrangulation that needs to be collapsed in the next keyframe. It needs to be gone. And then there's the location within the green part where a new face needs to appear. Now, this is where there's a fiddly bit of ad hoc combinatorics potentially, but the idea is that via flips, I will just take that face in the brown part and use flips around it to displace it and move it until it enters the green part, ends up at the right location, and creates a face where 1 is supposed to exist. And nothing else happens. The rest happens. The rest of the quadrangulation is left as is, untouched. All right. So hopefully you can believe me that you can create this sequence of flips with just the purpose of displacing this face. Okay, so, and now I should have obtained reduce k plus 1 of x on one side and reduce n minus k minus 1 of y on the other side. All right, so let's go back to my bird's eye view of the random path gamma of x, y. And let's bring back the formula that we had before, the Diaconis Salovkast kind of estimate for the relaxation time. So what can we actually do with that? I think the first thing I'll do is estimate the inverse of probability of the transition, which should be quite immediate because the probability of choosing a certain edge is 1 over 2n. And then, well, there would be a 1/3 for the direction of the flip, but really up to constants. No, that's not the first thing I'm doing, apparently. The first thing I'm doing is estimating how long this, this canonical path is, actually. So clearly I have n keyframes. And now here I'm not being very fancy with estimating how long it takes me via flips to get from one to the next. I'm giving an O of n estimate for the number of flips. In fact, it turns out, well, definitely you sort of flip each edge at most once. So at most it's going to be about n flips. As a matter of fact, it's going to be less than n flips, but let's do that. So we have n squared times the constant as my estimate for the length of my path gamma of xy. Now, all right, the constants I won't care about at all. You already have had spoilers, so you know that the bound is not going to be sharp, very probably. So I'll just change constants and call them C all the time. So the color of C will change because the constant will change, but we'll absorb everything in there. And now what's going to happen is what I was discussing before. That is that, in fact, the estimate for the inverse of the probability of a single flip is a constant times n, at least. So, all right. Now what's left is just the difficult part here. So the one that I promised would take a little bit to give an upper bound for, that is that sum of probabilities. And so let's finish by giving an estimate for this sum of probabilities. All right, we have a single fixed transition, an edge flip in a quadrangulation, we would like to know how much is this sum over xy of the probability that that edge flip appears in gamma of xy. And in order to give a bound for this sum, I sort of want to identify, given this flip, as much as I can about x and y, right? And the first step towards identifying x and y would be to identify in this phase, when this flip is happening, what is the brown part of this quadrangulation and what is the green part. Now, I cheated by drawing this quadrangulation of the sphere really lumpy, so it feels like I should be able to tell what the brown part and the green part are. In fact, there's a little bit of a trick here in the sense that if I do everything as I explained it to you, I am not able to exactly say what the brown part and what the green part are. I am only able to say that they must be separated by a cycle of length 2 that involves the root edge. But one trick that I could use is just waste one phase to make a buffer around the cycle separating the two quadrangulations in such a way that, in fact, I am able to immediately completely recognize the brown part and the green part. And I hope you'll believe me on that, but it's not that important. So let's say that I can tell what those two parts are. Now, let's suppose that the flip is happening within the brown, right? That tells me something very strong and clear about the green part of this quadrangulation, because I know that in the previous key frame, the green part is exactly the one that I'm seeing now. So assuming in the previous key frame, the green part has k faces, I know that it is precisely reduce n minus k of y. And now, what can I say about the brown part instead? Well, in the brown part, stuff is happening because I'm flipping an edge. But that edge flip, what it's trying to do is move a face along so that it leaves the brown part and goes into the green part. And here again, I'm lying only just a tiny little bit. There are constants involved, in fact, but I'm essentially able to identify which face is moving via that flip. And if I'm able to do that, I can just collapse that face. And I know that collapsing that face lets me see into the future, to the next key frame, where I will see exactly the map reduce k plus 1 of x obtained after I have moved that face away and into the green part. So what this argument just told you is that that sum is upper bounded by the sum over xy of the probability that reduce n minus k of y equals that green part of my quadrangulation, and reduce k plus 1 of x is equal to the brown part of this quadrangulation. And those two are completely independent. So I have this sums of all possible products, which is in fact a product of sums. And if you have put this formula somewhere in your brain, you know that I actually know how much that is. I find that I can give as an upper bound the product of Qn over Qk times Qn over Qn minus k minus 1. All right, so let's finally bring that back into our estimate, where we had a constant, we had an n cubed, we had a 1 over cardinality of Qn. We use ingredient 0. We know the asymptotics for the number of quadrangulations with n faces. And now what happens is that, well, the exponential parts will definitely cancel out. And the max in k of that expression is given by k being about half n. And what happens is that 2 copies of the polynomial correction cancel out and only 1 remains. So what you obtain is exactly the upper bound that Alessandra stated during his first talk. And now maybe I have 1 minute to say one more thing, a question that I would ask myself at the very least. So I'll ask myself a question first, that is, how do you apply this to other situations? And for example, could you apply this method to the triangulation walk, the first case that Alessandra discussed? We've already said that there's very little hope that this kind of method is going to work for lattice triangulations. Can it work for the triangulation walk? And the answer is yes. You can go through this idea step by step in essentially the same way. And what you're going to obtain is a factor n to the 3 exactly in the same way as before, and a factor n to the 3 over 2, that is the one given by the polynomial correction of the Catalan numbers. And now this quantity is n to the 4 square root n. Is that right? Yes, I think so. And the Tetali-McShine result that Alessandra stated for you was actually n to the 4 log n as an estimate for the relaxation time. You can do a little bit better with this. I already told you that the place I was most lazy was where I was estimating the length of canonical paths. And you could potentially shave off a further square root n and probably still have a log n factor in there given by the degrees of vertices. And I am pretty confident that you could get the Tetalian-McShine bound, but not that without any further ideas with this method, you wouldn't be able to get a better bound than that. And I think this is all that I wanted to say. We've been able to prove the upper bound. So thank you so much for your attention.
Thank you very much for your talk. So we can applause to thank you. We started over time, so you could have spent a few more minutes. It was so. Do people have other questions than your own to ask you? So if so, please feel free to unmute yourself and ask out loud. Yes.
Yes, thank you. Thank you for an excellent talk. Just one question. You mentioned actually the length of this gamma and so on. Does any of your result depend on the topology of the sphere? Say you mentioned that if you transfer it, say, to torus or any other object, does any of your result depend on the topology and say on the measure of the length of the path? Probably it's topological invariant, but just asking. Thanks.
So I think that you could repeat the argument in a very similar way, although you'd need to have all the ingredients. I know that people have worked on enumeration of, say, quadrangulations of on surfaces of different genus, and I think that you get similar enumeration results. But then if you wanted to apply the same method, you should also have these growth procedures that can be a bit of a pain to get if you don't have immediate bijective methods. So I don't know that it would immediately apply. I don't think there would be problems with lengths or distances. And in any case, this sort of method is going to give you polynomial upper bounds but not really sharp ones. So you don't care that much about the specifics of anything other than the things that need to be polynomials being polynomials. Then I hope that's a more or less decent answer to that.
Thanks. Yes, thanks.
Still about this question, I mean, in your proof, you need that gluing two spheres gives a sphere. If you glue two tori, it gives a genus too. So I don't know.
That is true. Okay, so you'd need to control something more complicated, I would say. Yes, so you have a point. This method of just growing uniform objects, it probably still would be fine. You open up your torus and just make a torus out of two cylinders. And yeah, no, I think that wouldn't be a problem, actually.
Okay. I see there is a question in the chat. I can read it maybe. It seems from what you say that there is an intrinsic problem occurring at the exponent 4, though you also say that's not supposed to be the right answer. Could you say something about that? The t to the fourth with log n, yeah, at the end of the talk.
Oh, okay. No, I think it's, so if the question is whether there's a reason why at the end of the talk we got the same upper bound for the relaxation time via this method, then the Titalian-McShine upper bound, and whether that has anything intrinsic behind it, I think that's entirely by chance. It's just you just get the same thing, but not because of the methods being similar in any way or because of something actually happening. I think it's very believable that the right kind of polynomial growth is n to the 3/2. It was just funny that you get the same.
Indeed. Yeah, so you are thanked by by Ivailo who asked the question. Are there other questions to ask to Alessandra? If not, I have one or two. If people think of other questions, you can ask in the chat. We will read them later. You mentioned that collapsing a face in quadrangulation, when we see it via Schaeffer bijection, it doesn't necessarily correspond to collapsing an edge at a leaf, that it was only the converse that was correct. Is it correct, however, that collapsing a face is equivalent to collapse an edge anywhere, maybe not at a leaf, or is it more subtle?
It's slightly more subtle in the sense that I hid some things under the rug. But the problem is, so you don't just have a tree, you have a labeled tree. So you have labels along the edges. And the reason why you like collapsing leaves better than collapsing any edge is that collapsing the leaf is not going to give you a problem with the labels. You'll just keep all the rest of the labels the same. But if you wanted to collapse an edge that is not a leaf, you would then have to deal with updating the labels along the tree if the labels of the vertices of the edge are different. And so there is something a little bit more tricky going on there, and it's much better to just deal with the leaves. Yeah. Okay,
I'm glad I asked the questions because I wasn't aware at all of. And just to know if there is some hope someday to be able to say something about 2p+1 non-simple angulation.
Okay, so you could go a bit further with this for sure, because there are still bijections that you can have with tree-like sort of structures for some situations, but general 2p+1 angulations I'm not aware of such good bijective results and precise enumeration results that would work in general. And I think that is kind of not small as an impediment towards using this kind of method. So, yeah.
I see.
You can probably do things directly on maps, for example. It makes sense. It makes sense that growth schemes should exist for those as well. But when you don't have as much control on the recursive structure in the same easy way, I'm not sure that it would be easy to show. That's.
I see. And I don't know well the topic of planar maps, but I had the naive feeling that for most problems, triangulations were easier than simple triangulations. And if I understood correctly, in your talk, it seems that simple triangulations are maybe easier than general triangulations. Did I understand well, or is there something going on?
That's not clear. I mean, that's what we decided to do. Flip-wise, okay. Probably non-simple triangulations is actually simpler, because for simple triangulations, then you have to be careful that you're keeping your triangulation simple, which not all edge flips will actually do. But for the growth scheme, we were working on simple triangulations in particular for the Poulalon-Scheffer bijection, and this we found this very nice link between blossoming trees and certain 4-array trees. But there are also bijections for non-simple triangulations, and I would expect that you can work on those and construct something there probably as well, but we haven't tried that actually.
Okay, thanks to that. And last question by Andrzej Straker again.
Thanks. Yeah, just one additional. Basically, you mentioned at the end the triangulation walk and related results. Basically, to what extent could your derivations be translated into a random walk perspective? Naturally, you could construct random walks on, say, the trees that you showed and so on, and possibly could be split also to some different, say, scaling limit results or similar issues which could be related to your talk.
So I don't know if that is what you're referring to, but for the triangulation walk, for example, there are scaling limits that end up being diffusions essentially on the space of continuous trees, and you can indeed work on these, well, not true, okay, conjectural scaling limits, in the sense that a related Markov chain has been shown to yield a scaling limit that is this diffusion on the space of continuous trees. But I think this area is extremely difficult to work in. Still, there are many technical difficulties with taking scaling limits of these random walks on trees or triangulations. I know some people are working on that. In that case, I think the walk that they've been working with is not really the triangulation walk, but something else for which there are sharp bounds for the mixing time. And the fact that we do not have sharp bounds for the mixing time of the triangulation walk or of the walks that I described on quadrangulations and other maps makes it so that I would not quite know how to go about passing to a scaling limit as a sort of continuous process on the scaling limits of quadrangulations and triangulations.
I think that precisely the paper that I linked during the Alessandra's talk from Holden and Soon, I think they researched the triangulations through the Brownian motion random walk processes and
Okay.
similar. Thanks.
I'll also have a look at that paper. Thank you very much.
Okay, and if we have no more questions, I guess we can thank both speakers again with a nice round of applause again.